No, I was getting like, when I very first started summing up everything, I was like, just sum it up.
Okay, let's start. Welcome to October. New month, but same announcements. There's a midterm in class this Thursday. It's going to cover everything we saw last week. So basically, it tells roughly the definition of back learning and batch learning and testing. It won't cover anything that I teach today. This stuff will show up for the final, don't worry. The important thing is please be here on time. I hope there will be about 150 of you here. I think there are at least 150 chairs. It will be really crowded, so please be here on time so that we can get things started. We'll try to be here at least 10-ish minutes in advance and make things, set things up. There are a few deadlines today. There's the project proposal milestone, spoken about it all this while. So I'm not going to talk about it. It's just you need to upload it to Canvas. And if you are doing the Kaggle thing, you need to do one other thing in addition to Canvas, which is upload a dummy submission on Kaggle, which is just a way so that you get the workflow set up. Make sure that you get the format right, and that you have an account on Kaggle. And on Canvas, you just need to submit a single document. It could be a text file if you want anything, with your Kaggle username, so that we know who made the submission. If you're doing a exploratory project, I've spoken about it before. You just need to write a document, no more than one page, please. That tells me what your project is, why it's interesting, and how it's related to the class. Many of you who are doing exploratory projects have already spoken to me about it, so I feel like I kind of know what you're doing, but please do submit a document anyway. As I mentioned in the last lecture, this proposal document is just the start of the conversation, and I'll, hopefully over the rest of the semester, we'll kind of fine-tune it and maybe grow or shrink the scope of this thing as appropriate. Any questions about the projects? We'll get to the midterm later. Any questions about project proposals? It's due midnight today. I understand there's like a ton of deadlines this week. So, on the bright side, it keeps you busy. Like I said, another deadline that's homework 2. Still not too late to start if you haven't started. You might finish it by today. It's mostly about the perceptron and linear classifiers, and most of you have some sense of what's going on. There's a lot of discussion on Canvas, there's the discussion board, and hopefully that should be helpful. Just wanted to bring your attention to homework 3, which will be available sometime in the next hour. I forget what time I set up Canvas to make it available. It's going to be, it's a quiz. I mean, it's called a quiz because that's what Canvas calls it. It's multiple choice questions that talks about everything that we did so far. In some sense, it's supposed to be something that can help you, that can guide your preparation for the midterm as well. That's why I wanted it out today. But it's due way after the fall break. It's due on October 23rd. You get 2 attempts. So, use it as you want. You don't have to submit it now. You will. Sorry. Okay.
Is it time bound?
Is it what?
Is it time bound?
No, it's not time bound. You can use what? It's mostly a way to kind of jog your memory. Yeah.
So is it meant to be something I can see? Like, are we going to see, like on the previous quiz, it was just like we got an overall grade, we had to guess which one we missed. Is this one going to have?
I don't remember. I will try to make it so that you get more fine grades as to what you got wrong. Right. That would be useful. I don't know if Canvas allows that. Do you know if Canvas allows that? It does. Okay, then I'll make it so that. Any other? It's one of the reasons why I wanted to bring this up before the midterm is because the midterm will also have some part of the midterm will look a bit like this. It will have some multiple choice questions, and I have been told that those questions, the flavor of those questions is that they can be tricky if you're not reading carefully. And I've tried to make this homework also that way. I still haven't made the exam, so I don't know what it is. So, any questions about these homeworks?
On homework 2, when I don't do the random initialization of the biases and vectors,
Right.
I get 100% accuracy on everything except the margin testing, and I feel like that's wrong.
I feel that that's wrong too. So, what do you mean by you get 100% accuracy on everything?
On the 10 epoch cross-validation,
There's some bad smell to that. How are you measuring errors? Maybe there's some. I wonder if there's a bug in your evaluation code, not in the learning code, but the evaluation part.
yeah, I'm trying to find where it is.
So one place where you could be measuring making a mistake is Okay, so let's kind of brainstorm this a minute, and then we can take it offline. One possible way that this could be a problem is if you measure error as y w transpose x is strictly less than 0 using evaluation. If you do that and you initialize the weight to 0, this is always going to be 0, so it is never going to be an error. So it's possible that this might be happening. So one thing you should keep in mind is during training, you should use something like this. If always use this for error during training and evaluation. If it's equal to 0, count it as an error. That might be a possibility. It suggests that's happening because if you measure error this way, this means that you will never make a mistake. Sorry, you measure error this way and W equals the 0 vector. That means it's always going to, y w transpose x is always 0. So I'm not literally knowing nothing about your code. This seems like the first thing to look for and see if this is happening. 100 is except for the mushrooms data set and any data set that you know is linearly separable, 100% accuracy seems wrong. Yeah.
Is it okay to get different file before you do this?
Absolutely. You might get different hyperparameters for different fields. So they tend to be close to each other. So one thing that typically happens with the hyperparameters is you find that the cross-validation, average cross-validation accuracy tends to be low at the extremes and high somewhere in the middle. So if I draw a bar chart of say, so this is whatever hyperparameter, and this is cross-validation accuracy. What you might get is something like this. This is one bar for the extreme, and then it goes up a bit, and then it kind of stays about the same. And depending on your random seed, you might end up with one of these three things. So the horizontal axis is different hyperparameters ordered, maybe say the initial learning rate, or maybe we'll see other things. And typically you get something like this. So as the hyperparameter at the extremes, you find that hyperparameter choices are bad, and the middle somewhere it's good. If you do not hit this, that means your extremes are not wide enough. But within the middle range, they are roughly equivalent, so it's okay.
In between epochs, should we randomize the order of
Yes.
the examples?
Yes, every epoch you need to shuffle.
Okay.
Yes. Other questions about any of these homework things? And by the way, that's true not just for perceptron, but for pretty much most learning algorithms. all a large fraction of learning algorithms that we'll see end up doing multiple passes over data for multiple epochs, and in each pass you have to shuffle the data. Yeah.
So when I don't shuffle, I am getting a higher accuracy when I shuffle.
That might be an artifact of this data set. I strongly recommend not doing that. In general, shuffling tends to be better. Okay, so those of you who just came in, reminder, these homeworks, this homework 2 that's due today. Homework 3 will be available today, due in a few weeks, but it's multiple choice questions and will look like some of the questions that you might see in the exam. So you have some incentive to take a look at it before the exam. There is an exam on Thursday, and there's a project proposal sort of thing that's due today. And of course, both for the homework and the project proposal, you get the extra 1 day that we spoke about at the beginning of the semester. Just to remind you, you get a 1 day, you can submit it 1 day late, up to 1 day late, and in exchange for 10% of whatever points you get. If you are more than 1 day late, you get no points. And that's a decision that you can make if, depending on how you want to play the game. Alright, my plan for today is to continue with Occam's razor, finish this part, and then maybe leave at least half an hour at the end of the lecture to kind of just do a quick overview of what we saw in the semester, so that if there are any questions that you may have about anything, we can use that time. Okay? So, in the last lecture, we looked at the PAC model of learning. Just to remind you, the PAC model of learning is this model for batch learning, where the idea is that we are going to give up on any expectation that we will find the classifier perfectly. Moreover, we are also going to assume that there may be some situations. So let me just write down the notation. So we're going to assume that any classifier that we have is going to have some error, and we're going to call that error. We're going to connect that error to a parameter called epsilon. Epsilon is essentially the maximum error we can tolerate. Let's put it that way. Moreover, there are some situations. Maybe we got unlucky with the data set that we were handed. There are some situations where even this error that we can tolerate is, there's no classifier that can get you this error. Maybe there are some situations, hopefully a small fraction of time, we might get unlucky and we end up with even the best classifier we can get has an error more than epsilon. And let's parameterize those situations by delta. So 1 minus delta is the probability that even best classifier is bad. And this might be because we got unlucky with the data set. And by bad, that means error greater than epsilon. This is the maximum error we can tolerate. So these are the two parameters that we can play with in PAC learning. And the definition of PAC learning says PAC learning is essentially, or PAC learnability is a property of a concept space, of a set of functions, of a concept, like Boolean conjunctions, let's say. So we call a concept class PAC learnable if, so there's a formal definition. For every error parameter epsilon, for every guarantee parameter, let's call it guarantee, delta, with high probability, with probability more than 1 minus delta, we will find a classifier that's less than epsilon. So it doesn't matter which data, sorry, I completely I said it wrong. So let me start from the beginning. So we call a concept class C PAC learnable if for every data set for that concept, there exists some epsilon and delta. There are some small numbers for which we can, with high probability, with probability more than 1 minus delta, we can find a classifier whose error is less than epsilon. That's just the definition. It's It's a set of concepts which are learnable, meaning high probability we'll find a good classifier no matter what the data set is. And no matter not just what the data set is, no matter what the function from the concept class is. So every function in the concept class is back learnable because with high probability we can find a good enough classifier. And so there are some nuances there, and so I will refer you back to the definition. But this is the intuition. With high probability, we'll find a classifier for every function. We'll find a classifier that's good enough, that has an error less than epsilon. Now that's back learnability, and this is an information theoretic idea. This is an idea that says there is enough information in a data set that will convey the classifier to a learning algorithm, to a reasonable learning algorithm. We're not talking about any learning algorithm that exists at this point. There is also the idea of computational complexity here, which says it's not just enough that the information is conveyed, there exists some learning algorithm which is efficient and it can recover the function with these guarantees. With high probability to find a good classifier error less than epsilon. So there is back learnability which says that every function can be learned with a good enough approximation can probably be learned. And efficient learnability is saying that a good enough approximation can probably be learned with an efficient algorithm. And that efficient algorithm, we'll call it the learning algorithm. So this is back learning, or this is the intuition. Any questions before we move on? What I'm going to do now is to point out, so first of all, I would like you to note that this is just a definition. We've just defined a concept class to be back learnable. Just like in the mistake bound model. We defined a concept class to be learnable under the mistake bound model. What I'm going to do now is to point out that this definition comes with formal connections to the idea of Occam's razor. So Occam's razor is simply the idea that you should try simple things first. Simple things that are that seem to work, that seem to be correct, simple things that seem to be consistent with your data are more likely to be correct. Because it cannot be by accident that a function that is simple fits so much data. So a simple function that fits a lot of data is more likely to be the true function. This is an inductive bias that we have. It's just this learning bias that we have because that we as a species seem to have. What we are going to do now is to make formal connections to this idea with back learnability. And I'm going to do this with a claim that looks more complicated in math than it is in real life. So let's say that we have m training examples. We have a data set with m examples. And suppose what we found is that, forget how we came up with a hypothesis, but let's say we have a hypothesis H. There is some hypothesis H inside this space of functions that we explore called capital H, the hypothesis space. So we found that this function perfectly agrees with all m of our examples. Meaning for all positive examples, this function says positive. For all negative examples, this says negative. Which means we'll call this function consistent with m examples. Now, let's say that this function is consistent with m examples and yet it has a generalization error that is very high. Error D of H. Remember from last lecture I told you that we defined this idea of generalization error, which is the probability of a hypothesis is the probability that on any example drawn from the two distribution, H of X is not equal to f of x. F is the true function. So this first point says that we have a function that perfectly agrees with m examples. The second point here says, despite agreeing with m examples, this function is bad. This function has a high error. Now imagine the surprise that you might have. Let's say that you have a classifier that achieves 100% accuracy with a million examples. Let's say And then I tell you, oh no, that can't be right. This classifier has really bad generalization error. That should be a rare thing. In fact, it's not just a rare thing. The probability that that situation happens is less than this quantity here. It's less than size of h times 1 minus epsilon power m. Before we prove this, let's kind of savor this. Epsilon is a small number, between 0 and 1. Epsilon, it's a probability. Or rather, it's an error parameter. So I'm going to remove this. Epsilon is an error parameter between 0 and 1. 1 minus epsilon is also a number between 0 and 1. Now, as m increases, so let's say m equals 1, let's say epsilon is 0.1. M equals 1, this will be size of h times 0.9, because there's only 1 minus epsilon is 0.9. Oh, that's not m. M equals 1, this quantity is size of h times 0.9. And m equals 2, this is size of h times 0.9, which is less than 0.9. As m equals 1000, this is size of h times a number between 0 and 1 gets multiplied with itself 1,000 times, it's going to be a really tiny number. Doesn't matter how big size of h is, this is going to be a really tiny number. So what this means is, as we see more examples, if your classifier is perfectly consistent with many examples, the probability that your classifier is going to have a bad generalization error gets extremely small. Does that make sense? Does the intuition make sense? So now let's try to prove it. Okay? So we're going to formalize Occam's razor assuming consistency, meaning that a classifier gets essentially zero training error. So we want to show that the probability that a classifier that is consistent with a lot of examples and is still bad is extremely low. Let's say that we have a hypothesis H that is bad, like the one that we think we have. A hypothesis H is bad, which means that the error of this hypothesis is more than epsilon. What does the error of a hypothesis mean? The error of the hypothesis is simply, so that means the error, so hypothesis error is simply the probability h of x is not equal to f of x is greater than epsilon. That's literally, I just restated what I wrote in English in math. The error of the hypothesis is simply the probability of the thing, which means the probability of h of x equals f of x has to be less than 1 minus epsilon. Right? So far so good? Okay? So what we have is that the probability that the function h agrees with the true function f on one example is less than 1 minus epsilon. This is with one example. But we know some other piece of information. We know that it's consistent with not one example, but it's consistent with m examples. And each of these examples are drawn IID. I didn't say this here, I mentioned this in the last class. IID is saying that every example is independently drawn from the same distribution. The probability that one event happens is less than epsilon. The probability that m independent events happen is less than 1 minus epsilon power m, because they just multiply with each other. Right? So the probability that the function that we have, the bad function that we have, is consistent with m examples is less than 1 minus epsilon power m. Now before we move on, I want you to ask me questions, because the next step could be a little surprising. Well, not surprising, yeah.
Is there any constraint on the examples, the policy of the examples?
Yes, there is a constraint. They are drawn from the same distribution and they are independent from each other. They are drawn independent, they are independent draws from the same fixed distribution. So the underlying assumption of all the theory that we build in batch learning is that your training set is sampled from a fixed distribution over the example. If a certain example is extremely highly represented, meaning every time you make a draw, you'll probably see the same thing. Like imagine weather in Antarctica. Most of the time you'll get cold. Imagine sensor readings for that are related to temperature and I don't know the amount of ice you can see in Antarctica. Most of them will roughly be the same. So those examples are much oversampled than say hot and red rock in Antarctica. So some kinds of examples will be oversampled, but we are assuming that these examples are going to be oversampled in the future also. In other words, the train and the test set are drawn from the same distribution. That's the only assumption that we have, and we have the other assumption. The follow-up of that is that they are sampled independently. Other questions? Yeah.
So can you go back to slides?
I go back to slides. What?
One more. Sorry. And one more. One more. Okay. One more. So, just now you wrote something on a blank, I think.
On a what?
On a blank slide.
What did I write?
If you wrote epsilon is the max error we can tolerate, and one minus delta is a probability. Even the best classifier is bad. It is supposed to be delta is the probability.
That's right. You're right. That's perfectly right. Yes. That's a good catch. Yes. Yeah. With 1 minus delta is the probability that we will find a good classifier. Yes. That's a very good catch. I do need my tea. So, yeah. So the probability that a bad hypothesis that has an error more than epsilon perfectly classifies. One example is less than 1 minus epsilon. The probability that a bad classifier is so lucky that it is consistent with m examples is extremely small. It's less than 1 minus epsilon power m. Now, this is one such bad hypothesis. Just one. Some bad hypothesis. We don't know which one. How many hypotheses are there in the hypothesis space? As many as the number of functions. Right? Let's assume that we have finite hypothesis space. If you have 3 functions, then there are 3 such possible bad hypotheses. We don't know which one's bad. Right? Any one of them could be bad. So the probability that there exists some bad hypothesis that's consistent with m examples is the number of hypotheses is less than the number of hypotheses times 1 minus epsilon power n. So, any questions? Yeah.
It's kind of hard to understand why the probability is associated with the error and not delta.
We haven't yet come to delta. So right now, the probability epsilon is the by the statement of this thing here, we are right. So by the statement here, we are saying that a hypothesis is going to be defined as bad if it has high error. In particular, we are going to define it as bad if it has an error more than epsilon. We are just going to define it that way. Epsilon, in general, in this in fact learning, epsilon is the error associated with a classifier, and delta is the probability that we find a bad classifier. It's associated with the act of finding a bad classifier. Okay, the event here is, did we find a good classifier or not? And that's the probability of finding a good classifier we are hoping is more than 1 minus epsilon. Epsilon is the error. Epsilon is in some sense the generalization is how much generalization error are we willing to tolerate. So we want a classifier whose generalization error is no more than epsilon. Sorry, no more than epsilon. Yeah.
Is delta kind of like a p-value? Is that
Loosely you can think of it that way. Yes. If you've seen p-values before, you can loosely think of it that way. Though I would not draw a formal connection between them.
Yes.
So why isn't this H minus 1? Aren't we assuming that there is one hypothesis that
Oh yeah, sure.
that does
Okay.
work?
Okay, fine. But it's still order of magnitude is the same thing. Yeah. We are building just a loose upper bound here. Yeah.
Just to be clear, this is an upper bound which can exceed 100%, right?
Which can exceed 100%. That's right. In fact, that's very good. Imagine that epsilon is 0.1 and the size of the hypothesis space is 1,000,000. The probability that some bad, this can exceed 1, and that which means that this is essentially a vacuous statement. Sometimes, yeah. Which is why this ends up being a vacuous statement if one of two things happen. If the size of H becomes extremely large, or if M is extremely small. And I'll give you a hint. This is where Occam's razor comes in. We want the size of H to be small. It's in our best interest to make size of H small, so that we don't have something vacuous. So, what we had, let me just quickly go through this again. The probability that one function is consistent, one bad function is consistent with f is less than 1 minus epsilon power m. Sorry, the probability that probability that some function named function x, let's call it h1, the first function that we encounter is bad, and yet consistent with one example is less than 1 minus epsilon, and the probability that it's consistent with m examples is less than 1 minus epsilon power m, because each of them is drawn independently, and the probability that there exists such a function that is bad and yet consistent with m examples is less than the size of h times 1 minus epsilon power m. And the size of h essentially comes in here because this quantity is added those many times. It's like a very, very loose bound. This is essentially a union bound, if you've seen union bound before. Okay? Now, that's basically a claim. It's not just a claim, I just proved it. The probability that there is a function, some function, we don't know what it is, that is consistent with m examples and still bad is less than the size of h times 1 minus epsilon power m. Now, in some sense, this situation is really what we don't want to happen. This is a situation that means learning has failed, right? Do you agree that learning has failed if we, at the end of learning, you come up with an algorithm, with a function, with a classifier that is consistent with your training data and yes, yet lousy? In that case, learning has failed, right? So this is, in some sense, the probability that learning has failed. It's a bad situation. Let's say we are interested in asking the question, when does this not happen? Because we want learning to succeed. In particular, we want to make this probability small. We want the probability of failure to be small. So I'm going to write something that is informal, but probability is from this lemma there, probability that learning fails is less than the size of x times 1 minus epsilon power m. Now, imagine that this was smaller than delta. If this quantity is smaller than delta, then the probability of learning failing is also smaller than delta, because I hope that's obvious. And we would like that situation to happen. In fact, we are interested in asking, what do I need to give the learning algorithm? What do I need to say about the number of examples and the size of the hypothesis so that learning does not fail, or learning fails with low probability? Let's say delta is the probability of failure. So, if this quantity is less than delta, then probability of learning failing is also less than delta. But now, notice that we have a term, an expression, an inequality that does not contain any word, it's just symbols, which means we can do algebra. Right? I can take log, So, and at this point, I'm going to first work it out and then bring up the thing. So let's start with this. So this is probability of is less than this, which is less than delta. And now we can ask, what are the conditions when for this to be true? I can take log on both sides. Log is an increasing function, so it preserves the inequality. So log size of the hypothesis space plus m log 1 minus epsilon is less than log delta. I've done nothing other than just, take log, and at this point there should be no surprises. There may be one little surprise coming up. I just have rewritten here the same thing here because there's a good chance that my handwriting is illegible to at least one of you. So, okay, now we have that. We've taken log, we have inequality. Now, what we do know is this log 1 minus epsilon is kind of an awkward thing, and I'm going to make one more I'm going to loosen this bound by saying, you know what, log 1 minus epsilon, and this is something that I want you to try to prove at home, log 1 minus epsilon is less than minus epsilon, when epsilon is small. You can prove this in many ways. You can prove that this quantity plus epsilon is negative. I'm not going to prove it, it's just a simple thing that you can think of it as a little puzzle. Log 1 minus epsilon is less than negative epsilon, so I can now get a much safer bound by saying I can replace, if I replace log 1 minus epsilon by minus epsilon, then that means this inequality is going to be, it doesn't always have to be satisfied, but you can ask, if this is true, if log size of the hypothesis space minus m epsilon is less than log delta. Notice that in the stuff that I write ln. That's just natural log. I'm assuming natural log here also. If this quantity is true, then if this inequality is true, then the thing on top is true. Why? Because of log 1 minus epsilon being less than negative epsilon. Okay? Is that, I don't know how much more detail you'd like, so if I don't get feedback, I'll just keep going. If what I've written at the bottom is true, then this is true, and this is just a restatement of this. So if what I've written at the bottom is true, then the probability of failure is less than delta. In some sense, the thing in the box here is a condition. If this is true, then the probability that your learning algorithm will fail is going to be less than delta, which means the probability of successful learning is going to be high whenever this quantity is true, whenever this inequality is true. Now, I can rewrite this. So, you can basically what you can do is get m on one side. So I'm just going to. I realize now that I should have planned this slide a little bit better because I want more space to write. So I'm going to continue this up here. I'm going to take m on one side and put all the logs on the other. So this is m epsilon is greater than log size of the hypothesis minus log delta. Is that right? I tend to make errors in algebra when I move symbols around, so please correct me. Means m is greater than 1 over epsilon log size of the hypothesis. Instead of writing log delta, I'm going to write it as plus log 1 over delta. They are the same, right? Log 1 over delta is the same as negative log delta. So, what I have here is something, a condition about the number of examples. If I have these many examples, so let me just number the equation. This is 1, no. This is 1, this is 2, 3, 4, 5. If 5 says, if I have these many examples, then, in fact, 5 is just a condition about the number of examples. It says m should be greater than this number, whatever it is. If 5 is just a restatement of 4, 4 is just a restatement of 3. Now, the way we came to 3 is, if this expression is true, then the probability of failure is less than delta. So 3, 4, 5 are essentially the same, which means if m is greater than that quantity on the right hand side, then the probability that your learning algorithm, whatever it may be, is going to fail is less than delta. So now what we have here is basically a condition about the number of examples we need. If you have these many training examples, and you find that there is a hypothesis that's consistent with m training examples, then you are kind of assured that life is good. So, very quickly summarizing the whole thing, and then we can go back if there are questions. Suppose you have a hypothesis space, H, and it turns out that you found a function inside that hypothesis space, let's call that little h, that is consistent with an entire training set of m examples. And this m is not a small number. In fact, it's larger than whatever this expression is. If you have these many examples, and you find that you find some hypothesis that's consistent with all of them, that means the probability that your learning failed is low. In other words, with high probability, with probability 1 minus delta, your hypothesis is going to have an error that's less than epsilon. Why? Because we just constructed this hypothesis that way. Questions before we go anywhere? Yes?
So I think you explained it a little earlier, but just to know if I'm understanding correctly, overfitting here wouldn't matter that much because we're sampling for some distribution that is representative.
Not quite. Overfitting doesn't matter because m is large. Overfitting doesn't matter because we have overfit a massive number of examples, which means we are most likely going to be right. And the ones where we are wrong is so rare because we have seen so much of the instance space that it doesn't matter. So overfitting does not matter if, one could say that overfitting an infinite training set is not a bad idea. If you have overfit everything that can possibly exist, you learn the function. If m is large enough, it's maybe not terrible. And by the way, that's a good observation. Being consistent with the entire training set could be overfitting because you get zero training error. Yeah. Yes.
I have a question on the previous slide.
Yeah.
Where you mark.
Yes.
So between 2 and 3, or when we say like log of 1 minus epsilon is less than minus epsilon, aren't we just increasing the value of LHS?
We are decreasing the value of the right hand side.
Because we are replacing log of 1 minus epsilon with
With
the greater value.
a greater value. Yes. Right. The top equation 2 does not imply 3. What I'm saying is, if 3 is true, then 2 is true. So it's actually a safer condition in some sense. If this is true, then that is true, but not the other way around, of course, because you're increasing the left-hand side. Yeah. So this is an argument that I must confess took me a while to see because of that point. Usually when we prove things, what we do is we make a series of arguments and we say this expression is true and we know some other piece of information, therefore the other next expression is going to be true. This is not that kind of a proof. Here we are saying equation 1 is true and 2 is true. They are the same thing. I have taken log. 1 and 2 are the same. 3 does not follow from 2. 2 follows from 3. So what we are saying is, if 3 were true, if this expression was correct, then we know that 2 is true. As a result, the statement, the the condition that we have is if 5 is true, because 3, 4, 5 are essentially the same. I've just reorganized things. I've just moved things on either side of the inequality. So 3, 4, 5 do not follow from 1, 2. All I'm saying is if 3, 4, 5 is true, then equation 1 holds, or inequality 1 holds, but not the other way around. But equation 5 is an easier to interpret form, which we will do in a minute, and that's why we're going to stick with that. So I have to tell you something. If you feel like you understood this perfectly, one of two things has happened: you already know it, or you don't really understand it. Simply because this is one of those concepts that needs some time to sink in. Go over it a few times. Make sure that you can kind of get the proof of the statement. Even the idea of what delta is, the probability of learning, succeeding, or failing, can be a non-intuitive concept. But I just want to spend some time interpreting this expression. We are going to show, this is the last thing I'll do today. I'm going to point out that this is essentially an Occam Fraser result. Yes? Yeah.
Yes, I have a question. The argument that if 3 holds, then 2 doesn't hold.
If 3 holds, then 2 holds.
Like, sorry, if 2 holds, then 3 doesn't hold, because, yeah, that's my question. Why are you making that argument?
Okay. Because this, I'm not saying it should not hold. 2 is a stronger condition than 3. Because what has happened here is this quantity is more than this quantity. I have increased the left hand side. So imagine the following situation, okay? Let's say this circle is a set of all worlds where 2 holds. 3 is a strict subset. This is 3 and this is 2. 3 is a strict subset of all the situations where 2 holds. Because m epsilon is more than log 1 minus epsilon. So we have increased the left hand side. Which means that, if you think of this as a number line, we have moved this closer to log delta. Which means there may be situations, like instead of thinking of it this way, for example, I can think of this is the number line, and let's say this is log delta, and this quantity here is say, the left hand side of 3 is something here. So this is LHS of 2, this is L. If the left hand side of 3 is less than log delta, then the left hand side of 2 is less than log delta, but not the other way around because we've increased it. So we have a stricter condition. There may be situations where we are in between those two, but we're not going to worry about that. This is a condition of the following kind. If we have these many examples, then learning will most likely not fail. However, it does not say anything about learning, succeeding, or failing if you don't have those many examples. Right? Does it make sense?
Yeah. So if,
go ahead.
If 1 holds, then 5 holds.
No, if 5 holds, then 1 holds. If 5 holds, then 1 holds. If 1 holds, in some cases, 5 might hold, we can't say anything. Yeah, it's the other way around. If 5 holds, then 1 holds. And that will kind of form the statement of the next slide. I have written the statement carefully to make it so that comes through. Yes?
So, in lemma 2, the part where it's less than or size of h1 and epsilon is all.
Yeah.
Would it be the same even for good hypothesis because all the points here are constants?
No, it won't. So, I see. So this quantity here?
Yeah.
Not quite, because in a good hypothesis, look at how we came up with that. So let's just let's see. So your question. Let me just go to a slide which is cleaner because it's just thumbnails, right? So how did we prove this thing? We assumed that we have a bad hypothesis that has an error more than epsilon, which means it's consistent with the probability that it's consistent with one example is less than 1 minus epsilon. The epsilon is in some sense the maximum error that a hypothesis can have. Sure, you can call epsilon as a constant, right? Epsilon is a constant, and it might hold. It might be the case that let's assume that some h is a good hypothesis. If it's a good hypothesis, we are defining the hypothesis to be good by saying that it has an error less than epsilon, which means all the inequalities reverse. So this no longer holds. Okay, so now I'm going to just interpret this statement that we have here, and let me restate this. Let's say we have a hypothesis space, capital H. And let's say we have a certain function, little h, that is consistent with m examples. The probability that this particular function, the function that we've learned, let's say h, that's consistent with m examples, has an error more than epsilon, is, let me first say what's here and then interpret it. So the probability that it has an error less than epsilon is going to be more than 1 minus delta. So the probability h has error greater than epsilon. This is an event, right? A learned function can either have an error more than epsilon or less than epsilon or equal. Let's just forget equality. It can be one of both sides. This is an event. The probability that this event happens is going to be extremely rare. It's going to be less than 1 minus delta. When will this happen? It will happen if we have enough training examples. If we have more than 1 over epsilon times log size of the hypothesis plus log 1 over delta number of examples. So the probability that a function is consistent with m training examples, x consistent with m probability that h and has error more than epsilon. Probability that this happens is going to be less than 1 minus delta if we have these many examples. Now going back to that other point, if we don't have these many examples, I'm not saying anything. Maybe you'll find a good classifier, maybe you won't. But if you have those many examples, then the probability that you will get a good classifier is rather high. Or rather, the probability that you'll find a bad classifier is going to be very low. It's going to be less than 1 minus delta. In other words, what we have here is that with high probability, with probability 1 minus delta, we will find a classifier that has low error, low generalization error, if you have these many training examples.
Are you making a mistake?
I might be making a mistake. So, oh man, yes. Yes, I keep making the same mistake. Yes, thank you. That's because of this epsilon. In the statement, I use error less than epsilon. Yeah. I would rather prefer writing it as the 1 minus delta form, so let's write it this way, as error less than epsilon. Happy? Happy also. Okay, so let's see what this means. This is a condition that says if you have these many examples, this is called the sample complexity. How many examples do we need? If you have these many examples, we'll find a good classifier. Suppose I demand that I have very low error. Expecting lower error increases the sample complexity. Why? Because the m is greater than 1, there's a 1 minus 1 over epsilon dependency. So if I demand lower error, that means the sample complexity grows. If I want a guarantee that you'll have low error, you need to show me more examples. If you have a larger hypothesis space, this makes learning harder. Why? Because there's a log size of hypothesis now. You need more examples to explore a larger hypothesis space if you want the same epsilon delta guarantees. Right? And if you want a higher confidence that the classifier that we have is good, then you need to show me more examples. So, there are 3 things that can make learning harder. If you want me to explore a large hypothesis space, then learning is going to be harder. In other words, the sample complexity is going to be more. If you demand that your classifier is perfect or very good, meaning epsilon is small, then your sample complexity is going to be larger. And if you demand a higher confidence in your classifier, then you have to come up with more examples. So in one shot, we connect the number of examples, the error of a classifier, the size of the hypothesis space, and the number of examples needed for the confidence of learning, confidence that you found a good enough classifier. Now, this is called Occam's razor because it expresses a preference for smaller hypothesis spaces. It says, if you want learning to be good with a fewer number of with a small sample size, then you are better off exploring a smaller set of functions. A smaller set of functions, in some sense, is simpler. So the simplicity part of the functions, it could be, maybe there are 5 decision trees in your hypothesis space, and each one of them has million nodes. It does not express a preference for smaller trees, it expresses a preference for a smaller set of functions. Exploring a smaller set of functions is, in some sense, easier from the sample complexity point of view. It's a better idea from the sample complexity point of view. It shows when, and I just made up this phrase, an M consistent hypothesis. It's a hypothesis that's consistent with M examples. This is a condition that shows that you can, if this condition is satisfied, an M consistent hypothesis will generalize well. It will have lower error. This does not mean that larger hypothesis spaces are bad. It's just that a smaller hypothesis class is more unlikely to fool us by being consistent with a large number of examples. It's the possibility that you have you only explored a small set of functions and you ended up finding, the possibility that you explored a small set of functions and you found a function that is consistent with a lot of examples is a rare thing. It's a rare event. And if that happens, it could not be by chance. Questions? Yeah.
I'm curious, does this apply to online learning as well?
Online learning is a different way of characterizing goodness of learning.
No, but we're not assuming anything here that seems to exclude that.
I'll give you 2 answers. We are assuming something here that seems to implicitly preclude that, namely that the distribution of the test in the plain examples is the same. We made no such assumptions with online learning. In online learning, there's an adversarial case. The examples could be presented by an adversary who is out to fool you. But keep in mind, even in online learning, at least with the halving kind of analysis, we found that larger hypothesis spaces are bad. Because even in halving, there was a log size of hypothesis that shows up. Across the various analyses of machine learning, one thing that keeps coming up, no matter how you seem to analyze it, is the idea that larger hypothesis spaces are maybe not the first thing you should try. So that was answer number 1. Answer number 2 is that it turns out there are these standard techniques for converting online algorithms to batch algorithms. What that means is there are standard techniques that if you give me an online algorithm, I will apply this online to batch conversion and give you a batch algorithm which comes with back guarantees. You've already seen one of those, which is the idea that you run perceptron, which came with a mistake bound, for multiple epochs. Running an online algorithm for multiple epochs is like a loosely online to batch conversion strategy. And then you need to do some work to prove some theorems about that. So now I'm almost done, so let me just wrap this up. We get a general scheme for pack learning. What you need to do is collect M examples. First of all, you need to collect, decide on a hypothesis space that is small enough. And let's say you're given M examples. And let's say you find a function inside that hypothesis space that is consistent with all the M examples. Now, if M, the number that you have, satisfies the condition, if the M is, that you have is more than the number of examples that theory demands, then you must have a good enough function. You must have a function that's close enough. But keep in mind, and this is important, pack learning, the formal definition of pack learning says the number of examples needed should be polynomial in 1 over epsilon, 1 over delta, and the dimensionality, D. I'm just going to call it D. Here we don't have the dimensionality, but we have log of the size of the hypothesis space, just like we had with knowledge. With mistake bound learning, the way I defined it, a concept class is mistake bound learnable if the number of mistakes made is polynomial in the worst case, blah blah blah, in the dimensionality. And then halving algorithm, I derived the bound that did not involve the dimensionality but involved the size of the hypothesis space. And I said, just because we have size of hypothesis space does not mean it's a mistake bound algorithm, because given a new class of functions, you need to count the number of functions there are. For example, with simple conjunctions, we had 2 power n conjunctions, log of that is polynomial, and so on. So we need to check that the number of examples needed is still polynomial in all these things, and if that happens, then the consistent hypothesis that we have is going to generalize well, is going to have a low error in the future. This is like a recipe for pack learning. It's just a conceptual recipe, it's not something that you can actually implement, but it's just a conceptual thing that you need to still work out details. You need to find an algorithm, first of all. This is just saying, could there exist an algorithm that can discover the function? I never said anything about how to find some function, I just said find some function. You need to invent a learning algorithm that actually does the finding. That's called the learning algorithm. For conjunctions, you can invent an algorithm that says that we already saw that the elimination algorithm, and we'll work out the details for conjunctions after the fall break. Any questions about any of this, some of this? This must hopefully be a heavy lecture. Simply because it's one of those things that I don't think you might see outside of the machine learning kind of context. So I would like you to revisit this, prove the math, because there are 2 levels to this. There is just the mechanical parts of this, just the proof. Those are the boring parts. Math works itself out. The more interesting parts are the intuitions. Why does the math work? What does the math mean? Try to think about that. And we will bring this up once again. Alright. If there are no questions, I'm going to move to midterm related things. Yes?
So today's content will not be shown on the midterm examination.
As of now, no, unless there's any strong demand. Okay. I think, no, it won't. So what I thought I would do is I posted a couple of documents on Canvas. One of them was just a review sheet. I'll bring it up. I called it What You Should Know. It's essentially what I have spoken about. This would be the stuff that we've covered so far, and the font is too small, so let me zoom in. This will be the stuff we've covered so far, and it's just something that you can use as a checklist when you're preparing. I also posted a sample midterm, and I realized that one of the things that you should not do is work at about 3 a.m. It turns out I posted one of the questions in the sample midterm was about nearest neighbors classifiers, which we've not yet covered, so you can ignore that. The questions in that document are just meant to give you a flavor of the kind of theory questions that the midterm will have, and that plus the homework 3 together would kind of roughly give you a sense of what kinds of things the midterm will have. Both homework 3 and the sample midterm that I posted are extremely long compared to the actual midterm. I understand that you only have an hour and some minutes, so I will not make you, the midterm should not take more than 3 hours to solve. Okay, so let's do a quick. You think that's a joke, don't you? Actually, no. So it turns out that if you are so the midterm will not be too, in terms of difficulty, it won't be any more difficult than midterms I've had in the past. And I've had two kinds of feedback. Some students have told me that was a trivial thing. Why did you not? Was it? For most students, tell me that took too long. So, your mileage may vary. But if you know all the answers and if you don't waste your time not knowing the answers, so the midterm should take you about 45 minutes. But of course, that's not going to happen. So let me do a quick review. And you can stop me along the way. This is just a couple of pages. I'm going to go through this and you can ask me questions. And I have office hours after this and you can stop. So at the very start of the semester, and for most of the semester so far, we've been looking at supervised learning. And when we looked at maybe the second lecture, I introduced the idea of what is supervised learning. You should know what are the different learning protocols and how they differ from each other and how changing the learning protocol could make learning more easy or more difficult. More concretely, you need to know what is an instance. You should know what's a label, what's a hypothesis space, and such things. We looked at classification and regression and multi-class classification, at least in definition. The only difference between these three things, in some sense, at a definition level, is the kind of labels that we produce. Classification or binary classification has, the label space has two elements. In regression, the label space is all the real numbers. Multi-class classification, the label space has k things. And an important concept that if you notice, we keep coming back to again and again, is the idea that learning is pointless if your hypothesis space is large. I gave an example of this with Boolean functions at the very beginning that pointed out, if your hypothesis space is all Boolean functions, there are just simply too many functions for you to possibly learn. It's just a pointless affair. An adversary could constantly keep flipping the labels and learning would never succeed. So you need to understand why we need to restrict the hypothesis space, even without using the language of fact learning that we just saw. And then you need to understand what are the general issues that you have in learning, namely the choice of a hypothesis space, the choice of representation, meaning the features. Changing the features could make or break learning. And then there's a learning algorithm. The learning algorithm is, at the end of all this, just a procedure that takes your data set and produces a hypothesis. Some learning algorithms come with guarantees, and those are the ones that are interesting. The first concrete hypothesis space that we looked at was that of decision trees. You need to know what a decision tree is, what kind of functions they can represent. You need to be able to understand how to make predictions in the decision tree, and you one useful thing that maybe we didn't spend enough time on, but it's kind of a good thing to know, is how many trees can exist given a certain number of features. This is not a trick question. It turns out this is how many trees. One question that could be interesting is how many trees of a certain depth can exist. For example, if I restrict you to trees of no more than depth 2, how many possible structurally different trees can be there? How many Boolean functions can be there? You need to know how decision trees deal with continuous features. The answer is rather simple. With continuous features, you kind of bucket them, or you somehow threshold them, or do something like that. You convert them into discrete somehow. We looked at one learning algorithm for decision trees, which is the ID3 algorithm. You should be extremely comfortable with the ID3 algorithm. The ID3 algorithm relies on concepts like entropy and information gain. You should be able to, in some sense, implement the algorithm on paper, step through the algorithm essentially. And you should understand what is entropy, you should understand what is the information gain, what is the intuition. The ID3 algorithm is a heuristic. I call it an algorithm. It's really a heuristic that favors shorter trees but does not come with a guarantee that it will find the shortest tree. You should understand why shorter trees are a good thing and use intuitions about hypothesis space to justify this. We looked at overfitting for the first time in the context of decision trees, and this was where the training error was low, but the generalization error is high. Of course, the overfitting applies to other classifiers also, but you need to understand, not just for decision trees, but for all hypothesis spaces, what are techniques to deal with overfitting. With decision trees specifically, perhaps the most popular technique to deal with overfitting is to not grow the entire tree. The idea is that you restrict the growth of the tree to, say, some particular depth, and this, because you're only exploring trees of no more than a certain depth, your hypothesis space is smaller because there are fewer trees of certain depth, and as a result, you generalize better. The ID3 algorithm was originally defined with entropy, but that's not the only way to do it. There can be other measures of, in some sense, impurity, and you can redefine the information gain for other measures. You looked at one of them in your homework, the majority error. Speaking of which, I'm hoping to have homework 1 graded and back to you tonight, and hopefully by then you'll also have the solutions for it. So, with decision trees, you also need to understand how to deal with missing features. Sometimes your data may not have all the features, and so you need to understand how you can, there are standard techniques, you need to infer what is a way to, how do you deal with it, because the tree can't break down. The tree, you can't make a prediction if you don't know a certain feature, and you need to figure it out. And you also need to know when to use decision trees. Now this is more of a question of taste. When do you use decision trees? When you want an interpretable classifier. Think of the connections between linear classifiers and decision trees. A decision tree is more human understandable. If I give you a million-dimensional linear classifier, and I tell you this classifier made a positive decision, it's slightly harder to understand because the features may be harder to interpret, and it gets harder with other classifiers. Decision trees are perhaps the most interpretable hypothesis space out there. Okay? Any questions about any of these things so far, by the way? I mean, I can keep talking, so if there are questions. Yeah?
It's a midterm closed note.
Yes. The midterm is closed notes, closed laptop, closed iPad, closed phone.
Should we be expected to remember the equations for entropy?
So, not really. I want to, my memory is bad and I try to not expect that from other people. So anything you need should be in the exam. Of course, that doesn't mean that it would hurt to remember it, but you should not. I'm not expecting you to remember it. Then we went to linear classifiers. Yes,
So for the decision trees, should we memorize the ID3 algorithm?
I expect you to know the ID3 algorithm. Yes. And it's not a question of memorizing. I'm not going to ask you to write down the ID3 algorithm. I'm never going to ask you to write down any algorithm. I might ask you to analyze a variant of the ID3 algorithm. So you need to know how ID3 works. So the point of this is a teachable point, not with you, but in general. The point of the midterm is not to test memorization, but generalization. So I will expect you to generalize beyond what we just saw. Because otherwise, it's just remembering. And we know very well that if you remember, you're not going to do well in the future, and that's what matters. But anyway, yeah, so I do expect you to know it. I do expect you to, for example, sniff out any bugs I might have in a faulty algorithm, for example. But I don't expect you to memorize complicated formulas. Like the pack formula that I showed, we don't have that for the midterm, but that's complex enough that I don't expect you to memorize. We looked at linear classifiers. You need to know what's a linear classifier, what does it mean to be linearly separable, what kinds of functions can you express with linear classifiers. We looked at the geometry of linear classifiers, and you need to understand that pretty well. The idea of feature expansion or feature transformation, how do you convert a function that was not linearly separable into something that might be linearly separable in a different feature space. We saw an example of that in the class, and I expect you to understand that idea. We looked at regression, least mean square regression, and in particular, I introduced the idea of learning by minimizing a cost function using least mean square regression, and you should understand that idea. And we looked at a couple of algorithms for this, in particular gradient-based algorithms and stochastic gradient descent. So we are coming close to the end of time, so I have only 2 minutes. I'm going to just rush through this, and if you have questions, you can find me afterwards. You can use Canvas, or I have always asked. We looked at mistake-bound learning. Mistake-bound learning is just a way of asking how good is your learner, and under this framework, we looked at the general structure of what an online learning algorithm may look like. Learning proceeds in rounds. The learning algorithm sees an example, it makes a prediction, and then it gets feedback about its prediction, and then it can make an update, it can make a correction. The goal of mistake-bound learning is to count the number of mistakes and show that the number of mistakes is going to be small. This defines a class of algorithms called mistake-bound algorithms, and this defines properties of concept classes as being mistake-bound learnable or not. A generic mistake-bound algorithm is the halving algorithm, which is, you should be able to prove how many mistakes the halving algorithm makes on a finite hypothesis space. You should be able to use the result for specific classes of functions, which means you should be extremely comfortable with counting the number of Boolean functions, simple Boolean functions, like the examples that we worked out in class. We looked at the perceptron algorithm in quite a bit of detail. You need to know what the algorithm is. No excuses not to know the algorithm because it's basically about 3 lines, at least the insides of it. It has a certain geometric meaning. You should understand the geometry of the perceptron update. Every update essentially rotates the hyperplane to be closer to correct. One of probably the most important things with the perceptron algorithm that we saw was the Novikov theorem, which is essentially the mistake-bound theorem. You should be able to prove it. You should be able to extend it to minor variants of the perceptron algorithm, because the proof proceeds in 3 steps. Every perceptron proof proceeds in 3 steps. You first prove an upper bound, a lower bound, and then kind of sandwich the things using something like Cauchy-Schwarz inequality. Every perceptron proof proceeds in 3 steps. You should be able to extend the proof to minor variants, which means you should know some minor variants of the perceptron algorithm. We looked at averaging, the margin perceptron, and such things, and the batch version of it. And when it came to learning theory, everything that we did till Thursday, which is basically you need to know that the what is the definition of batch learning, you need to know what the definition of back learning, what's efficient back learning, you should know the ideas of sample complexity and computation complexity of learning. Alright, I think I'm going to stop now. I'm a minute over time. I have all class, so I'll move on.
What's up? That is